which I have verified is working as I stare at the little green bar that is tracking my microphone this time. Very important to have the microphone turned on while recording, I have learned. But here we go. Homework 2 went reasonably well. I had a peek at the pattern of incorrect answers, and it looked like there were 2 questions in particular that seemed like folks had problems with. But are there any that you want to ask me about before I do those?
I'm not sure which ones you would be referring to, but I was wondering if we could go over the last ones about invalid effect sizes.
Those would be it. Yeah, that's where I was go. So yeah, I'll scroll down to the bottom here. So several of the questions are going to be custom based on whatever data results you found. So whether a given correlation was significant or not significant, positive or negative. The last 2 are true of everyone because everyone has the same story as part of their design. So which of the following, number 52, is true about Pearson's R as a linear relationship between age, which is binary, and classroom teacher, which is also binary? So binary predictors can be treated as quantitative variables. Sorry, predictors. They're variables in this example here, just variables. They can be treated as quantitative because there's only one unit between the 2. So if you talk about what a 1 unit change would be in the context of a linear correlation, you're moving from a 0 to a 1. So there's no problem in making an inference about that because there's not more than 1 unit that you'd have to decide whether it's equal interval or not. So it's just 0 to 1. So it is okay to do it. The correct answer is that it is limited by range restriction caused by the variable means. So there's actually a slide about this in lecture 2. It discusses the idea that in binary variables, the mean and the variance are not separate things, the way that they are for other types of variables. So the normally distributed variables, for instance, the mean and the variance are separately estimated parameters. In almost every other distribution that I'm familiar with, the mean and the variance are tied together in some fashion. In binary variables, the mean, the proportion of ones times the proportion of zeros is how you compute the variance. So that means that in the middle of the variable, in terms of its possible values, when a binary variable has a mean of 0.5, it has a variance of 0.25, which is the most it can have. And as you move away from that mean of 0.5 in either direction, the variance that corresponds to that necessarily shrinks. So the closer you get to the extremes of the mean, the closer you get to the binary variable being a constant. And that means that there is a corresponding shrinkage in the possible covariance that two binary variables can show. So only when both variables have a mean that is 0.5 is there a possible maximum Pearson correlation of 1 the way they're supposed to be. Otherwise, it's going to be some value less than 1. So that was the idea that I was trying to convey with this first answer here. So in practice, a Pearson correlation is a valid measure of effect size between 2 binary variables, but it's not an ideal one. A better version would be something that's known as a tetrachoric correlation, which is not something we have time to talk about, but it's something that gets used for binary variables when they're part of models in advanced coursework. So does that answer your question about that one?
Yes. Yeah, your explanation makes sense. I guess what I'm struggling with is remembering when we talked about, or like where to like find like in like the PowerPoints where we talked about whether an effect size is valid or not. I just couldn't remember that.
It wasn't on a direct slide, but the implication of it in terms of whether it's valid or not is just whether the idea of a linear relationship makes sense.
Okay.
So for instance, the last one here, a linear relationship between fits thrown and favorite TV show. So fits thrown is a quantitative variable. In this case, it's actually a count is the way that it's distributed. So it's integers that don't have negative values. But favorite TV show is a nominal variable. So even though 1 is Peppa Pig and 2 is Paw Patrol and whatever, they're not really numbers. So from that perspective, it doesn't make sense to talk about a 1 unit increase in TV show because more is not better. Like you can't say that, you know, the TV show that is number 3 is better than the TV show that's number 2 is number 1 because it's going to depend on the child's idiosyncrasy. So what would happen instead, if we wanted to look at a relationship between fits thrown and favorite TV show, that's the one case we didn't talk about yet. This was foreshadowing how you would do that, which is in the context of a model. So that is starting the next unit, lecture 4, is going to address that situation, how you would indicate a bivariate relationship between TV show and fits thrown, so nominal versus quantitative. So everything else that I asked you to do is valid, so to speak, with the exception of, for these last questions here, for instance, for favorite TV show, enter the mean. That makes 0 sense. I wanted you to be looking at it and think about it like when you're computing these things, and realize that SAS and Stata will be happy to do things for you that make 0 sense. It don't care. So that's on the analyst side, to make sure that what you're doing is reasonable. So that was sort of the point of asking for those values, is to then make you think, wait a minute, like, what am I doing here? So those were the two that I saw people had missed most often. Are there questions about any of the others, or why the answers are the way they are?
I had a question about 51. I selected significantly positive instead of non-significantly positive. And I'm going to be honest, I think I kind of guessed on this one, but I knew it was positive. So is there a certain variable I should have looked at that I used, or not variable, value I used earlier that I should have used to figure that out?
So question 51 was referring to results that were up above. They are right here, these two questions. So teacher and age, I asked you to find the Pearson correlation. So the sign of that Pearson correlation would tell you whether the correlation is positive or negative. And then the next one, enter the p-value for the Pearson correlation, would tell you whether or not that correlation is significant if p is less than alpha, so less than 0.05, or non-significant if p is greater than or equal to 0.05. So this is an instance which would have been based on your particular data, but the way that I generated the data is that in the population, those two variables were unassociated. So I believe all of you would have had non-significant correlations, but they may have been positive or negative based on how it shook out. So the way that the homework system runs, by the way, is that each of your 8-digit IDs is the random seed that I use in generating your data set. So each of you has a custom data set. Even though the data were generated with the same population, each of you is a different sample. So it's the same logic that underlies all of this stuff. All right, does that help, Alex? Yes? Okay. Other questions on any of these? Okay, then homework 3 is available. You should be able to do about half of it right now. We haven't talked about the estimate statements, and we haven't talked about binary predictors. I'm expecting to get through all of that today, so then you'll be able to finish that. And then you have a formative assessment due next week. So homework 3 isn't due for 2 more weeks. So we're well ahead of the homework schedule, which I had made generous just in case things went awry, because it's hard to know what to predict, especially in current times. So, all right, we good with this then? All right, then bye-bye and welcome back to the beach. Tell me what you remember from last time. It's been 5 whole days, right? Today was garbage day. That means it's Tuesday. What did we start talking about?
We talked about SAS and Stata code for general linear models.
Yeah. So what are general linear models for? In what situation would you use one of those?
When you're trying to figure out what the impact of a variable is on an outcome.
Yes. What kind of outcome specifically? Quantitative or categorical?
Quantitative.
Quantitative, yes. So the idea of general in the term general linear model is that you're predicting an outcome variable whose residuals are supposed to be normally distributed. So that should at least be a quantitative variable to begin with to make that plausible. What kind of predictor? What kind of predictor variables can you have in general linear models? I'll make it a multiple choice question. How's that? So the kinds of predictors you can have in a general linear model are quantitative only, categorical only, or whatever you want.
Is it quantitative only?
If you want to call it a regression, that is true. But
That's what I wanted to do. So
Yeah.
it's just great. You know.
Yeah, and if you wanted to call it a nova, then it's categorical only, but the general linear model subsumes all of those special cases as one thing. So actually, yeah, it's whatever kind of predictors you want. So they can be quantitative variables, they can be binary, ordinal, nominal, it can be whatever you want. So we're talking about, so far, just linear relationships of a quantitative predictor of a quantitative outcome. But we're going to generalize that to binary predictors as a special case of quantitative, and then in the next unit, look at ordinal, nominal, and nonlinear effects of quantitative predictors as well. So yeah. Let's see. Let's do definitions. These are things that you should try to get committed to memory as quickly as you can, because it will make it easier to track what follows. If I talk about beta 0 as a model intercept, what does that idea refer to? What's an intercept?
Where the line crosses the y-axis.
So where the regression line that is reflecting the slope of how x relates to y crosses the y-axis. So the intercept, beta 0, fixed intercept because it's constant, is always the expected y value when x is 0. So to make sure that the intercept is something meaningful, what do we need to do to x? A linear transformation that starts with a C.
Center.
Centering, yeah. So we want to make sure that x, the predictor variable, has a scale with a meaningful 0. And one way to do that is to center it, meaning to subtract a constant, which changes where the mean of the variable is. So some value towards the middle is often picked. A minimum value would also be a reasonable thing. In the next set of examples, I do that for an age variable, for instance. But the key idea is that you want to keep your intercept within the scale of the data, because it represents the you are here reference point of the model, to which all slopes are then relative. So as we talk about the effect of a 1 unit increase in x, it's like, well, 1 unit more than what? More than what is what the intercept gives you. And what about a slope? If I had beta 1 as a slope of x, how do I define that? And I will take words or gestures. What's a slope?
I think it's easiest to remember it as the rise over the run.
Yeah, that's 8th grade algebra language, rise over run. I would also take this gesture of my arm moving up and down. So a slope is the extent to which the extent of the increase in y for a 1 unit increase in x. So the change in y for a 1 unit change in x, or the difference in y for a 1 unit difference in x, you can say it any of those ways. If an x variable is completely unrelated to a y variable, what would the slope be? Yeah, 0 or flat. What's the maximum slope that you could have? Yeah, Fayaz, you're half right. The question you got to ask me is, are you talking standardized or unstandardized? So if you want to say standardized slope Phi
It's one.
It's 1, yeah, because then you're in a Pearson correlation metric where you go from -1 to 0 to 1 as the full range of what the slope is. But if you're talking unstandardized, what's the maximum slope that you could have? Is the correct answer. Infinity. Because unstandardized slopes are in the units of the variables. So if you want to talk like change per millisecond or change per year or change per inch or change per pound, the unstandardized slopes are in the units of the original variables. So we can test them for significance. We can say whether or not it's positive or negative, which conveys the direction of the relationship. We can say whether or not it's significant given the sample size. But to get a more absolute sense of how strong the relationship is, yeah, we need to convert it back to some kind of an effect size. So that's the role of a standardized slope, is to put the slope back onto a Pearson correlation metric of -1 to 1. Okay, one more definition then. What's a residual?
The epsilon, the end of the equation, like whatever is, we don't know.
Yep, it's E or epsilon, depending on your notation. My philosophy with notation is to never pick a symbol I can't draw with like complete accuracy, and that's why it's E and not epsilon. There's for certain Greek letters I stay away from too, because I can't draw those either. I call them squiggle 1 and squiggle 2 because I never learned them. So E is what I use, R is what some people use, epsilon is what we use. But yeah, so if I told you to define a residual, what does that E or epsilon represent?
It's the deviation from the predicted amount.
Yes.
The error, but you don't like the word error.
Yeah, I don't like the word error because it makes it sound like it's wrong, but it is unexplained variability. So you could call it a residual, you could call it a deviation, you could call it an error. Those things are all used synonymously. But the key idea is that it's how far off your outcome is from the one that's predicted by the model. So if your outcome in reality is higher than what was predicted, your E will be positive. If your outcome was lower than what was predicted, your E will be negative. So the mean of the zeros is actually what is given by the regression line, or the fixed effects in the model. And do we care what E is for each person, or do we care about some sort of summary measure across people instead?
A summary measure?
Summary measure. Yeah, we want the variance of the E's across people, which has a special name, which is residual variance. And this is where we started learning how to find this stuff on the output. So scrolling through example 3 here, we did univariate stats, we did some measures of association. So we did an empty model, for instance, just stopping by page 4 here. An empty model is a pedagogical tool. It's not something that you would necessarily estimate for general linear models in life, although in other contexts, like the longitudinal class after this one, we do start with estimating empty models. The idea here is that the empty model represents all of the variability in your outcome that there is to be predicted. So it's a baseline with which to compare subsequent models. The only effect that is in it to build the model is beta 0, the intercept, which means that our best guess for each person would be the mean of the outcome. And then from there, we make a better guess by customizing that mean as a function of one or more predictor variables. So at this point, 190 as it shows up on the output. So mean square column, and then it's called error in SAS. It is called MS for mean square, and residual in Stata. That 190 represents all of the reasons why some people have a higher Y outcome variable than others. In this example, that happens to be income in $1,000 units as what we're talking about predicting. The best guess for each person is the mean of income, which is 17.3 in this example. And then we looked at adding education, but education wasn't centered, which resulted in an intercept that was out of bounds for what income could possibly be. So then we centered it and looked at the results. So I think this might be a good place to pick up with the rest of the story. So any questions or things you want to talk about more before we dive back in?
So Lisa, when you put in a variable, the residual MS tends to change. Is it possible for it to go up?
Yes.
Okay. So
Uh,
there are the variables that can make it more ununderstandable.
It would only as a consequence of something that we haven't talked about yet. So this column right here, sums of squares, is the numerator of the variance equation. It refers to the amount of information that is left over, but then that gets divided by the denominator degrees of freedom. So if you have a variable entered as a predictor that has no relationship whatsoever, then it may not reduce the total information that's been captured, but it does reduce the degrees of freedom, and that can result in a net increase in mean square error, although that is very atypical. I have seen it happen. Generally speaking, mean square error will stay the same as the worst case scenario, and it should go down to the extent that your variable that you've entered as a predictor has any kind of relationship with the outcome. That is why when we get to talk about our square, which I've sort of danced around but haven't introduced formally, that is formed using sums of squares rather than mean squares to avoid that exact problem. In further models that are not estimated using least squares, models that are estimated using maximum likelihood instead, which is like every other kind of model besides the general linear model, sums of squares are not there, and what you'll get as a direct estimate is just a number that says residual variance. And so in those cases, they behave in a similar fashion. They could go up, but usually would not. Thanks for the question. Okay, other questions before we dive back in? All right, so I want to show you sort of two ideas here. The process of entering a variable as a predictor, which is something you'll get to practice in homework 3. So the first step is to make the predictor variable. So we have a column called education in the data set. I want to create a new column next to it or down the road from it that is education minus 12. So I have to do that first. So here is the point where I'm making it in SAS. The name of the new column is what goes to the left of the equal sign. So EDUC12 is my new name because I have centered education at 12. You can name it whatever you want. My convention is to put the centering constant at the end of the new variable name. That way I know automatically what 0 means. And that new variable is what goes into the model. So in terms of troubleshooting this process in your homework, the very first question that I'm going to ask you for any model is, what is the residual variance? That's mean square error. If you don't have that right, you don't have the right model, meaning you do not have the right predictors designated as an outcome or predictor variables. If you have a mean square residual right, but you don't have the fixed intercept right, so if your fixed intercept is wrong, but you have the right model, what that means is that your predictor variable is not the right centering. Because the intercept is the expected outcome when x is 0, it would mean you have the wrong version of x in your model if your fixed intercept is not correct. So I try to ask those two questions to help you make sure that you have everything right to answer the rest of the questions. So education centered at 12 is the new predictor variable that goes into the model. And I believe we looked at the results for that last time. Here's the slope for education. So note that we have two fixed effects in the model as given by this table. Each fixed effect has its own estimate. The first column, or coefficient, is a synonym for estimate. That's also known as point estimate because it's one number. The next column over is its standard error. So the intercept has a standard error, the slope has a standard error, and each of those standard errors conveys the expected inconsistency of that estimate across repeated samples of the same size. So it is an error in the sense that it's noisiness, right? it describes the extent of expected fluctuation based on, say, chance or just expected randomness in these variables. So we have each term here, each parameter as they call it, intercept and slope of education, has an estimate, has a standard error. If we take the estimate, divide by the standard error, that gets us to the third column t. So like t of 11 here, that's our test statistic. By the way, the other class, I figured out how to turn on live transcript of myself talking at the bottom of the thing here. I have several students who requested that, so I can turn it on for this class if you want, although I have to have my phone to block it. But they told me that whenever I say test statistic, it says fish sticks. So I'm watching to see. Apparently it's learning me because it's not saying fish sticks anymore, but this is a test statistic and not a fish stick. So, anywho, does that help to have it on, or is it distracting? It helps? You like it? Okay, we'll leave it. We'll leave it, and I'll put my phone in front of it so that I don't have to watch myself say fish sticks. Okay, there we go. So yeah, technology is wonderful. By the way, if you didn't know, it takes a few days, but every time I post one of these class videos to YouTube, it generates automatically a transcript so that you can watch the words play next to the video. It does a pretty good job, and they're searchable. So like you can do a search through the transcript for homework question, for instance, and find the spot in the video where I talked about something. So technology can be very useful. All right, there's blocking the phone. All right. So then 11, the fish stick, as it were, the test statistic, that is a standardized way of expressing how far away a given parameter estimate is from the null hypothesis. So in this context, if I'm looking at the slope of education, the null hypothesis I'm testing it against is that the slope is 0, meaning flat line, meaning no association between education and income. The t-value of 11.28 tells me that my obtained slope is 11 standard errors away from the null. The exact p-value that goes with that t is less than 0.0001, so with less than 0.01% of the time, I would expect a slope this extreme if the true slope were 0. So this is definitely in significant territory. Reject the null hypothesis. It's significantly positive based on the coefficient itself. So t and the coefficient will match in sign. For every additional year of education, so for every 1 unit change in x, the amount of predicted income goes up by 1.82. So more education, more money, as it were. So then this fixed intercepts. Yeah, go ahead.
Can you explain why you picked 12 for the center? Like, would it matter if you had picked 8 or 16, or why did you do 12?
I'll answer the second part first. It would matter only with respect to this fixed intercept right here. So if I picked 8 instead of 12, the fixed intercept would then become the expected income level for somebody with an 8th grade education, which would be 4 units down from where it is now in terms of where the slope is. If I had picked 16 instead, then it would be the expected income for somebody with 16 years, and it would move up. So it only changes the interpretation of the intercept. It would not change anything else in this particular model. The slope would be the same. The amount of residual variance left over would be the same. To answer your question, then why 12? Because 12 has a ready interpretation. 12 years of education corresponds to a high school degree, whereas 16 years of education could be a bachelor's degree if you never changed your major and went to summer classes to get all your credits in, like I did. But if you didn't have quite as much certainty, it might take you 5 years to finish a bachelor's degree. So what is very commonly done in creating predictor variables with meaningful zeros is something called mean centering or grand mean centering, where you would subtract the mean of the predictor. However, in this context, the mean of the predictor, if memory serves, was something like 13.8 years. And so then my reference point for the intercept would be 13.8, which I'm pretty sure is an answer that no one wrote down. Like nobody says they went to 13.8 years. So in thinking about a meaningful reference point, like what kind of person is this the intercept for, 13.8 is weird. But there's no wrong place to center, there's only weird. The intercept just moves to accommodate wherever that 0 point is in the scale of the variable. In more advanced models, centering at weird places can actually cause estimation problems, but that's not going to happen here. Thanks for the question. Okay, other questions? All right, so this intercept then, one way of looking at it is as the reference point for the model, which is the way that I've been talking about it. Another is saying that this is one of any infinite number of possible values of income predicted by education. This happens to be the prediction for somebody with an education of 12. But what if you wanted to know what it would be for somebody who has 13? How could I use these two numbers right here to come up with a predicted outcome variable for somebody with 13 years of education instead of 12? What would I have to do?
Plug that into the equation then?
Plug it into the equation. Jerome, are you making hand signals at me? Because I can't, you got to raise your hands up if you're doing that. No? You're good? Okay. Yeah, plug it into the equation. Like right here. So I can do the math right here. Like for instance, if I wanted to know what it would be for 8 years, I plug in a -4 where education was. Now, why is it -4 and not 8?
Because you centered it to 12, so -4 from 12 is 8.
Exactly. This is something that people screw up a lot. So I'm making a point of emphasizing this. It's -4 because 8 is 4 less than 12. So you would plug it into the centered version of the variable. And I can put this into my calculator or my phone or Excel, right? And I can get a 6.7. But what I don't get as easily, although there are formulas for it, they're more painful, is its standard error. So if I wanted to get some sort of range of expectation, like a confidence interval or something, I'd have to do additional math. So I want to help you learn how to make the programs do this kind of additional math for you. So more generally, this code that's up here, which I've broken down below, estimate statements in SAS and lincom statements in Stata, these are ways of asking the program to compute linear combinations of fixed effects. So not only does it compute the result of the linear combination, but it computes the implied standard error for you as well. And it does hypothesis tests built in. So I'm actually going to scroll down to the Stata version of this because theirs is more directly intuitive as matching the equation. And then we'll look at what SAS does. So right here, these statements right here. In Stata, this is page 7, by the way. You remember what this thing is, folks who are learning Stata? _CONS?
Constant?
That's the constant. That's Stata for beta 0. So I'm saying in plugging in this to my regression equation, I need one beta 0. So beta 0, if you think about it as a slope, it would be multiplying a column of 1s. So in the matrix versions of these models, you would need to add that to make the math work out. So the 1 is here sort of conceptually to represent that and also to make it look like the SAS code, although it's not strictly necessary. And then we add in the variable and the value that we want for it. So here's the catch, what makes this tricky. When I type EDUC12, what I'm actually telling Stata to get is the resulting value of beta 1. So internally, it's going to read constant and go, oh, she wants beta 0. Okay, what did I find beta 0 to be for this model? It was 14. Okay, cool. And then, oh, she wants the slope for education 12. Okay, that was 1.8. All right, let me do the math for her. And then that is the result of the regression equation. So if I want it for 12 years, this line here is included just for pedagogical purposes because that's what the fixed intercept already gives me. If I want it for 16 years of education, I would put in a 4 because 4 is for more than 12. And if I want it for 20, I would put in an 8. So the way that Stata writes this makes it look exactly like the regression equation, where constant is the beta 0 and education 12 is the beta 1, and then the value after the asterisk is the amount of the predictor that you want the predicted outcome for. And so Stata annoyingly, unfortunately, puts these all in separate tables, but it repeats whatever you told it to say. And so the result of that linear combination was estimated as 6, and it gives me the standard error, and it gives me a hypothesis test, even though that's not relevant for predicted means, and it gives me confidence intervals. So if you wanted to, say, make a figure illustrating the results of your model, and you wanted to show predicted values with confidence intervals around them, this is a technique that would allow you to do that. So you can get predicted values for any level of your predictor variable in terms of what the model says it should be. So then we have for education equals 12, which is just the fixed intercept for the model again, and then 1 for education to 16, then 1 for 20. So then SAS code is very similar but less explicit because there's no plus signs and there's no multiplication signs. So to do the exact same thing in SAS, I've written out the 4 equations that are being recreated by these 4 lines of code. So instead of constant, you have to write the word intercept. And what SAS is doing is saying, oh, she wants what beta 0 is going to be. That's going to be the 14. I want one of those because I need one beta 0 included in every person's predicted outcome value. And then education 12 is whatever beta 1 turns out to be in the data. So that's the 1.82. And then I tell it for what level of education I want the prediction. So you'll get a chance to practice these on your homework. And then here's the resulting table. Just like up above, we have an estimate for what the predicted value of outcome is going to be, a standard error for each one, and then a t-test and confidence interval. And this is what is not in the SPSS version of GLM, at least the last I checked. I check about once a year so I can make sure that to change my notes if it's incorrect, but it doesn't have this. So that's why I can't teach these models with that software. Okay, questions on any of that? No, we're good? Good enough? Any that you want to hear again? Or hear differently? Or do you got it? Got it? All right, cool. Now, further interpreting what the model says, here are some pictures that you can get spit out for you in SAS GLM, for instance. This is a histogram of the E's, the model residuals. So these are the values of the discrepancy, how far off each person's actual outcome was from the outcome that's predicted. So here is the regression line on the picture on the right here. E is the difference between each of these little bubbles and where the line thinks the little bubble should be. That's what E is. So residual variance is the variance of these E deviations across people. And this is a distribution of the E deviations. And the red line is the best fitting line to the observed distribution. The blue line is the line that would be predicted if these residuals had a normal distribution. And it looks not that terrible. It doesn't, I mean, it's not perfect, but it's a lot better than it used to be. So do I have that? I don't think I have that. Let me scroll back up for 1 second here to the marginal distribution of these variables. Here it is. So this picture right here on the left, that's what the distribution of income as a variable looked like before we did anything to it. So that's what's known as its marginal distribution. That does not have to be normal. It needs to be at least quantitative to have a shot at being normal, but that doesn't have to be normal. What is supposed to be normal to believe in these results is the distribution of the residuals. That's supposed to be univariate normal, this one right here. And you won't know if it's normal until you fit a model and check out the residuals. So we'll talk, I think next time we'll probably get to that, sort of what are your options if it isn't normal. And I'll just tell you now, your option is get a new model. The option is rarely fix the data to make it normal. You want to pick a new model. If it doesn't fit, get a new model. But that's what GLM is supposed to be, is this idea of a normal distribution for the e's that remain. They're also supposed to have constant variance and to be independent. So there's 3 big assumptions that we'll talk about with respect to the e's. All right. Comments or questions on that? No? All right, then I'm flipping back to introduce another type of predictor besides just the quantitative one, how we would enter a binary predictor in the model. And I know that there's one slide that's going to be messed up because it always unsaves itself every time I do this lecture, and I have yet to figure out why. So I fix it manually each time, and I make it work. There. Right here. So slide 23. Lecture 3 is where we're picking up. So it says, what about categorical predictors? Well, I told you like a half hour ago that you can have any kind of predictor that you want in your general linear model, and that is indeed true. So we'll start with an example of just a binary predictor, and then next unit, we'll talk about how you would do an ordinal one and how you would do a nominal one. So the basic idea of putting in x as a predictor variable does not change at all if you're talking about x as a quantitative variable versus x as a binary variable. It just takes a little bit of logic in wrapping around what it means to have a 1 unit increase in x, because what that actually means for a binary predictor is going from a value of 0 to a value of 1. So more generally, you will need to include fixed slopes that are c minus 1 with respect to the number of categories for c. So if I have a binary variable, c is 2, that means I need 1 slope, because I will have a fixed intercept that gives me the predicted outcome for whichever group is denoted 0, and then I will have a slope that gets me from the 0 group to the 1 group. So the first step then is to take whatever binary variable that you have and make sure that it is coded such that one of the groups is 0 and the other group is a 1. So this is known as dummy coding, colloquially. It's also known as contrast coding sometimes, although that latter phrase refers sometimes to a coding of -1 versus 1. I don't like that kind of coding in most cases because then 0 doesn't exist as a reference point. 0 versus 1 is much more interpretable to work with. So that means that, cough, cough, homework question. When you do this in homework 3, you'll be looking at age as a predictor using the same data as homework 2. So you have age 3 and 4. That means you'll need to center age so that one of the groups is the 0 and the other group is the 1. And by the way, what I'm about to tell you is also known as a 2 groups or independent samples t-test. So that is yet another special case of the general linear model when you have a binary predictor of a quantitative outcome. So for instance, if I have a variable called married group, whether I have people who are not married versus married, and let's say that it's coded such that 0 are the people who are not married and 1 are the people who are married. So this coding is completely arbitrary. In this instance, you don't have more versus less. They're just two kinds. But we still have to represent one of the groups as 0 so that we have a meaningful intercept, and then the slope talks about what happens to the alternative group that's coded 1. So Mary 01 then would be the version of the variable that I put into the model in which 0 means unmarried and 1 means married. So given that coding scheme, my beta 0 fixed intercept always going to be the expected outcome when the predictors are 0. When this predictor is 0 means for somebody who is unmarried. So that type of person, that category, is now my reference group for the model as the intercept. Beta 1 is always the difference in y for a 1 unit difference in x. A 1 unit difference in x corresponds from the tradition from the 0 unmarried group to the 1 married group. So a simpler way to say that is that the slope beta 1 is the mean difference. It tells you how much different the mean for the 1 group is from the mean of the 0 group. And then E is still the residual. It's how far off the predicted outcome variable is from the outcome predicted by the model. So in this case, it would be the difference within groups around their own mean, because each group would get the same predicted mean, and E is how far off you would then be from your group's mean specifically. So the regression line, the output that we're going to look at, looks kind of funny because I've got 0 people over here for the unmarried group, and I've got 1 people over here for the married group, and then I've got a whole lot of space in between where there's nobody. That's okay. It looks weird, but it's still okay. So the results of the model that we're going to look at in SAS and Stata, we can say that the regression equation here at the top, the intercept works out to be 14.45, so that's the predicted value for the 0 group. So if I want to fill in what y would be for the unmarried group, I'd put in a 0 for the predictor and it stays 14.45. Then for the other group, I would put in a 1, and the slope was estimated at 6.22, so that means the married group makes about $6,000 more than the unmarried group in this example. And unlike other kinds of quantitative predictors, for a binary predictor, you can only have a linear relationship because there's only one possible difference between 0 and 1. So that's all you can do, is just talk about the mean difference of the 1 group relative to the 0 group. And then for an effect size, because we're talking about groups and how their mean outcome variable differs between groups, it's less intuitive in this context to use R as an effect size for a standardized slope, and it can be more intuitive to use an effect size that reflects mean differences. So the classic example of this is what's known as a Cohen's D. D for difference. So Cohen's D tells you how many standard deviations apart the two groups are, where the two groups have to share a variance. And so SD pooled in this case works out to be the residual variance of the model. So the square root of the residual variance is SD pooled when you only have one group as a predictor in the model. There's a bunch of kinds of these. So people have come along and tweaked this formula and added their name to it. So here's a couple examples of that. But the concept of a D-type effect size is still valid. It's still standard deviation units apart. You can get a D out of the T test statistic. So 2 times the T value that you get divided by the square root of the denominator degrees of freedom. That's how I'm going to get a D out of the output that we have, because the output gives me T and degrees of freedom, and I can get D from that. And more generally, here are some formulas by which you can go back and forth. So as long as you have a T and you have degrees of freedom, you can get yourself an R, or you can get yourself a D, or you can get back and forth between the two. So all of these measures of effect size are related to each other. And this is helpful to try and put the size of the difference into some kind of more standardized fashion. we go back to the example. So we'll see this, how the code happens to make that work. Still in education, here it is. All right, so this is what we're doing. So I'm on page 9 of example 3 to show you what this looks like inside the programs. So first step, make sure that your binary predictor is coded such that somebody is the 0 and somebody is the 1. So in my instructions, I will tell you which should be which, but the code for this looks a little bit different. This is a more general way of doing it such that that could be extended to more than 2 groups, which is why I'm introducing this here. Let me move this thing out of the way. There we go. So in SAS, for instance, these 3 lines are necessary. So I'm first generating a new column that is blank. So Mary 01 is going to hold the new version of the predictor that I'm going to be creating, and I'm setting it equal to dot, which refers to a missing value. So I am creating a blank column that I am then going to put values in. Then I'm using conditional logic to conditionally fill in that blank new column. So the new column comes in the second half of the statement in SAS code. So in English, what this is saying is that if the column I already had, which was called Mary, equals 1, then in the new column I just created, fill in a 0 instead. So for those people who used to be a 1, make them a 0 in the new column. For those people who used to be a 2, make them a 1 in the new column. So the reason that I did this initial step of initializing it and making it blank is to make it look like the stata code in which this is necessary. It's not strictly necessary in SAS, but conceptually it also makes it so that if there's some other value, so like if somebody for whatever reason doesn't have a 1 or a 2, they had some other value, they stay at a dot. So that way we don't accidentally copy over values that are incorrect. So this code here only deals with the 2 scenarios of interest. Anyone else would have missing data if they're not a 1 or a 2. Also make sure that this value and this value are different, because otherwise you'd write over your column of data and possibly screw it up in doing so. So anytime that you want to make a new version of a variable, put it in a new column. So Mary 01 is the new column. Mary is the column it's pulling that information from. Okay, with me so far?
I have a question, Lisa.
Yeah, and then Fayaz, you can go next.
Okay. Oh, sorry.
Yeah,
Yes,
you
I didn't mean
first.
to cut you off. So on our last homework, we had a variable that was already sort of coded like this. Like I don't know what it was for others, but for me it was teacher, like whether you had like who's teacher. And I understand that we didn't necessarily use that as a predictor variable, but I'm noticing that is this like a similar process? Like I'm just trying to figure out like what the difference is between that and then what we're doing here.
It is exactly the same.
Okay.
Oftentimes in publicly available data, you will see binary variables automatically coded as 0 versus 1 because they know that this is coming and they're trying to save you a step. If you have a survey where it's like the first answer is 1 and the second answer is 2, then you end up with some sort of ordinal thing like this one where you'd have to convert the 1s and 2s to 0s and 1s. In your homework, it was Beth was 0 and Molly was 1. And then in the next iteration of homework using that same data, you'll have to take the age variable that was 3 versus 4 and turn that into 0 versus 1 to use as the analysis. Otherwise, the intercept would refer to a 0-year-old, which is somebody you don't have in your data set. All right, Fayaz, did you have a question too?
So when you are when you are creating a new variable, Mary 01, and putting the dots in there, so are the dots in place of NA values?
It starts as dots. If
Okay.
if it's a 1 or a 2, the dots get replaced with zeros or ones. But if it were any other value, they stay as dots.
Okay, so they are being used instead of what you would see in R as NA values, right? Not like missing, like they don't represent anything.
In R, it would be NA is what it looks
Yeah,
like in the data.
yeah.
Although I don't know if that's a code or whether that is a string. I'm guessing it's a code of some kind.
It's a string. I'm not sure. Yeah, I don't. Yeah, I
Okay,
think
yeah.
it's yeah.
It's not there is the general category, and each software
Okay.
package has a different way of saying not there.
So the dots don't actually carry any value in this. Okay, makes sense. Yeah.
No, it's a missing value of a quantitative variable. So it would have to be something else if it were missing and it were a string. Yep, good questions. And then, of course, a label on here as good hygiene. Let me, before we look at output, let me do the stata code because it looks
I have
very
one
similar,
quick
but it's
question too.
backwards. Yeah, go ahead.
So is the only reason then you're coding it into 0 or 1 is just to make it easier to look at?
To make the intercept easier to look at.
Okay.
Yep, because then the intercept directly gives you the mean for the 0 group, and then the slope gives you the difference for the 1 group. So the slope would be the same even if you left it as 1 and 2, but the intercept would be off.
Okay.
Yep. And there's no wrong way to do this particular variant of coding. So the stata version looks very similar, but the ordering of the conditional statement is backwards. So the first step is make a blank variable. So gen a new column called Mary01 equals dot. And then it's replace the new column if the old column is 1. So in SAS, it's like if the old column, then do this to new. In stata, it's do this to new if this is old. So it's just a transposing. And the other thing is this right here, these two equal signs, that's not a typo. So stata has two different versions of equal. If it is one equal sign, that means make it that way. So turn this into a 0. And if it's after an if, then this is evaluating an equality. So if Mary equals 1 is evaluating that as being true or not. If it's true, then the replace of the 0 value in the new column happens. So evaluating an equality is 2 equals, setting something then to a new value is 1 equal sign. M+ uses the same coding scheme, by the way, in terms of 1 equals versus 2. I've seen that a few other places as well. So that's the only tricky part, is that the if comes at the end in stata rather than at the beginning. So since we're here, we'll stay with stata and then go back to SAS for a moment. So regress, the outcome variable comes first, the new predictor variable comes second, the comma denotes options for what gets printed, so I'm asking for 95% confidence intervals, and then my two lincoms. So the model already gives me the predicted outcome variable for the 0 group, so the first one is technically redundant but included here for pedagogical reasons. The second statement then gets me what the model says the 1 group's mean would be. So then I have all 3 pieces of information. I know what the 2 group means are predicted to be for my outcome variable, and based on the slope, I know whether those 2 means are different. So putting it all together, the mean for the 0 group, which is unmarried in this context, people who are unmarried in this sample are predicted to make $14.4 thousand a year. If you are married, so relative to the 0 group, the 1 group is higher or lower? What do you think? Relative to the 0 group, is the model telling me that the group coded 1 is higher or lower in their outcome mean? Plus, is that what this is? Higher? Yeah. That's what the coefficient being positive implies. The one group is higher than the zero group. So I'm trying to say this very deliberately because it's easy to be lazy and say this is the group difference. But you don't know how to interpret the sign of the group difference unless you know who the reference is. So the reference is the 0, is the 14. Relative to the 0 group, the one group is higher by 6. So people who are married are predicted to make about $6,200 more a year than people who are unmarried. And this is personal income, not household income, by the way. Is that a lot? Is $6,000 more a year a lot? That's a lot of money. I can have a very nice vacation with $6,000 or maybe get a used car or something, but is it significant? Yeah, where do I look for that? I'll take arrows. Yeah, my T and my P right here. So the slope, 6.22, that's the slope. The standard error for this slope is right next to it. Take slope divided by standard error, that gets me to T. So yeah, my slope is like 6 standard errors away from the null hypothesis of 0. So p-value less than 0.001. Yep, confidence interval for that slope does not include 0. So I'd say the slope is significantly positive. So putting all of that together, I would say that people who are married are predicted to make significantly more money by $6,200 than people who are unmarried. What if people who are married were predicted to make less money? Then what kind of coefficient would I have? Yeah, it'd be negative. Yep. So the slope coefficient tells you how the one group differs from the 0 group.
Can I ask a question, Lisa, just to make sure I'm understanding it? So the reason we're highlighting this is because it could be tempting just to look at like the 6 and 14 and say, like you want to make sure that we're not interpreting it as like that's how much difference this is, because the constant being 14, that's technically like the 0, right? So we're not really comparing like the 6 to the 14 in the same way.
Correct.
Does that make sense? Okay.
I think so. So the 14 is a mean. The 6 is a mean difference.
Okay, yes. They mean different things.
Mm-hmm. And
okay.
If I take the 14, which is for the 0 group, and I add the 6 to it to get to the difference, to get up to 1, that's what this Lincom statement is doing for me.
Okay.
It's coming up with the predicted mean for the one group. That is down here. So there's the 20 for the one group. And question, since T and coefficient will have the same sign, could that also be used to determine positive or negative relation? Yes, in this case. So when you're only testing one thing, meaning you can use T for it, the sign of that one thing and the sign of T will match. So that is true for T and that is true for Z. When you're testing more than one thing, using either chi-square or F, those are squared units. And so those values are only positive, which means the sign will not necessarily match what you're testing. But, I mean, I can look at these numbers and even in my head, figure out that 6 and 14 are 20. The reason to go to the trouble to make the software do it for you is that it also computes the standard error for that prediction, as well as a hypothesis test if that's of interest. So you get the additional level of specificity from asking the program to do it. And answering a question that I'm not sure that you asked, Mackenzie, but I'll pretend like you did. To interpret this 6, right? Is 6 a lot? It's all relative to the standard error. So because the standard error is 1 for that slope, that means that the slope is 6 standard errors away from the null. If the standard error for this slope were 5, for instance, if my slope was 6, and I'm like, well, that sounds like a lot, but the standard error is 5, then is it really 6? It's like, no, it's going to be off from 0 by 5 on average. 6 is well within expected fluctuation. So a slope of 6, if the standard error were 5, would be just past like a t of 1. And that wouldn't be then a trustworthy a lot. So it looks like it's a big slope, but it's super noisy. And that's what would happen if you had a smaller sample. The standard error is a function of two things. In addition to the scale of x, it's a function of the sample size, and it's a function of the amount of residual variance left over. Those are the things that go into standard error. So all things being equal, a slope estimated on more people is going to have a smaller standard error than the same slope estimated for fewer people. All right. Other questions? All right, then the SAS code that goes with this. Same exact ideas, but in SAS language. So we have the name of the data set as something that you'll have to change for your homework. Outcome variable goes to the left of the equal sign, just like it does in the equation. Predictor variable goes to the right of the equal sign. And then that new predictor variable is what gets used in the estimate statements down here. So this is asking for the predicted mean for the 0 group in the first line, which is redundant but included again for pedagogy. It's the second line that needs to be here to get the predicted mean in the 1 group. That's a linear combination of the fixed intercept plus the fixed slope times 1 for that predictor. So then that additional output shows up down here. And here's the effect size for that slope. Here's the formula. So 2 times the t-test statistic for the slope divided by the square root of the denominator degrees of freedom. So 2 times my t of 6.25, it's 732 denominator degrees of freedom. That number, by the way, is right here. So it's under DF, there's 2 listed. The first one under model is what's known as numerator degrees of freedom. That's the number of slopes in your model. That's going to be 1 in this unit. Error then is the denominator degrees of freedom. It is the number of slopes you could have added but didn't. So because I have 734 people in this sample, I estimated a fixed intercept and I estimated a fixed slope to create my regression line. So I spent 2. That means I could spend up to 732 more. So that's where that number comes from. I did that in SAS by opening a data set and asking it to do math and then printing the name of the data set. So that works out to be a D of 0.46 as an effect size. So the difference in income of married people relative to unmarried people corresponds to a D effect size of 0.46. So they are roughly half a standard deviation apart. That's your D. And here is here's a picture of the residuals after including marital status. Again, not exactly normal, but much better than what it was to begin with. And then stata, you can make it do math to do the effect size as well with this word display. Okay, questions on that? So I have included for this little results section 2 versions of this last result right here. So the first paragraph describes the analysis of education as the predictor. And this paragraph describes the inclusion of the binary marital status predictor in a regression kind of language. So in that way of looking at it, we would refer to what the intercept was, we would refer to what the slope was, and talk about the slope being significant, And then as sort of an afterthought, we would describe how the slope and the intercept translate into a predicted income for the one group. So the emphasis would be on the 0 group and the slope that conveys the difference. Whereas if I had reported the exact same analysis but called it a 2-sample t-test, the way that I would talk about it is, here's the mean for one group, here's the mean for the other. I have a t-test of their difference, where that's the t-test statistic for the slope. So then we have, the difference itself is not given directly, just the means are given, but the test of the difference is given here. So it is the exact same thing, it's just a different way of talking about it. All right, how are we doing? Good? Feel like you can do this? I think you can do this. In fact, I know you can do this. So then we have effect sizes in terms of different types of predictors. If you have a quantitative predictor, an R-type effect size, so a standardized slope, is usually more intuitive because then it talks about the change in Y for a 1-unit change in X in standard deviation units. If you have a binary predictor, then a D effect size for how different the two groups are in your binary predictor, it tends to be more useful than an R, but they're all telling you the same thing, just using different metrics. D is not bounded. So a D of 0 corresponds to no difference, but it can go into positive versus negative infinity. It's not constrained to 1 and 1 like R is. So different scale. All right, I think that was, yeah. So then just one more thing here. I ended up making this picture after the fact and answering folks' questions, and so I thought I would just make it and go for it here. The idea of how test statistics and slopes and effect sizes all relate to each other. So you can think of any relationship between variables as having an effect size. So that an effect size corresponds to a standardized version of viewing the relationship, always in standard deviation kinds of units. So we have a null hypothesis oftentimes that there's no effect. That's on the left-hand side of this picture on slide 27. And we have, some possible continuum where there's some highest level effect that you can have. And then there's the line in the sand. So this blue line here is meant to convey where unexpected starts in terms of how we would talk about this effect size. If we have p greater than or equal to our alpha level, we would say that the effect size is not significantly different than 0. So 0 is within the range of expected fluctuation based on the standard error for whatever this effect size is based on. And if we cross the line, p is less than alpha, we would say that it's significant. The location of this line is dependent on sample size. So if I have a very large sample, the line moves this way. It makes it easier and easier to say that a small effect is different than 0 because it's expected to wiggle a lot less across samples. If I have a very small sample, it moves the line this way. Then it becomes harder and harder to say that a given effect is different than 0 because it's really noisy across samples. It has a very large standard error. So that's why even though we may have a significant slope and we may be able to talk about it in terms of, $6,000, having some kind of effect size to go with it is the missing piece of information that we have to convey, because some things could be significant just because of a big sample and not because it's a strong relationship. And given that all of these slopes are in unstandardized units, standard error is one way to contextualize it, translating it into an effect size metric like D is another. So, all right. Questions or comments before we adjourn for the day? Nope. We're in good shape? All right, then we're actually ahead of schedule. Hooray. So we'll do the last of this bit, what choosing the GLM means, and then we'll actually get to start the next unit. So I'll move those slides and stuff up to be there for Thursday. Hooray! All right then, Have a good day. Hope to see you Thursday. Take care. Let me know if you need anything. Peace out, y'all.